You all know what different phases of matter look like. Let's just say we've got some solid and we try and put on some magic spectacles and see what it looks like. The solid particles will be positioned very close to each other in a little clump all together. If, on the other hand, we had some liquid, we would have the liquid in a container. The particles would be pretty close to each other. They would be down at the bottom of the container, and that would be what your liquid particles look like. Your gas particles would fill the entire container, and let's say the screen is the entire container, and there would be particles all over the screen. They would fill exactly the space of, let's say, the screen. It wouldn't matter if the particle sizes, now let's look at particle size, and what if I decided to enlarge the size of these solid particles? So I'm going to have 5, but I'm going to have 5 bigger particles over here in a little clump. As you can see, that occupies more volume. Same would be true if I were to look at liquid particles and make those particles bigger, 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 bigger. And those are right next to each other. Actually, they're supposed to have little spaces, so maybe we would fill up even more volume like that. But what about if we did the same thing to the gas particles? Let's make that one big, that one bigger, that one bigger, that one bigger, and that one bigger. What you see is that actually it makes no difference to the actual volume of gas. On account of that, actually, gases have got a fixed volume. And the volume depends on how many particles there are. Because what actually makes up the volume of gas is the spaces between. So the space is what comprises the volume of a gas, not the actual particles. So gases have got fixed volumes depending on how many particles there are. Now we know that we're going to measure particles in what are known as moles. Now we've got a unit, it's called a mole of matter. And it turns out that if we are at a temperature called STP, and STP is called standard temperature and pressure, and that means that we are at 1 atmosphere, and we are at 25 degrees, sorry, not 25 degrees centigrade, 0 degrees centigrade. And at standard temperature and pressure, all gases, regardless of what gas it is and what size the particle is, will occupy 22,4 decimeters cubed of space. Now that's a handy thing. It's called a molar gas volume. Let's tell. So 1 mole of gas occupies 22,4 decimeters cubed. That's given to you on the information sheet at standard temperature and pressure. And therefore we can say the number of moles, let's say I had let's go with 11,2. Someone gives me 11,2 decimeters cubed of gas. You agree? That's half a mole, because 1 mole is 22,4. And therefore you land up with an answer of 0,5 moles. How do I abbreviate that? V over Vm. I can get a triangle for that. Number of moles is equal to volume over molar volume. And we've got the units that we measure it in is, once again, we look at moles, cubic decimeters, and molar volume is measured in decimeters cubed per mole. So how many moles, we've just done this one, are present in 11,2 decimeters cubed of gas? Number of moles is equal to volume over molar volume. This should say at STP. If they forget to say at STP, I'm sure they mean it, because you can't really work it out at any other temperature. There are, by the way, equations where you can, but we don't do them at school. 11,2 and 22,4, and then you land up with the number of moles being 0,5 moles. What about 7,1 grams of chlorine? We're looking for a volume, but we've been given a mass. What are we going to do with that? We're going to go number of moles is equal to mass over molar mass, which is 7,1, and chlorine gas, remember, is Cl2, so it's 35,5 plus 35,5, which is 71. I get 0,1 moles. Then I can say the volume is equal to number of moles times molar volume, which is equal to 0,1 times 22,4, and I land up with 2,24 decimeters cubed. A Calculate the number of moles of substance in each of the following. Press pause, try work through these, and then take a look at the answers. So, if you've got 2,24, volume is equal to, number of moles is volume over molar volume. And therefore, I divide that by 22,4, and I land up with 0,1 moles. And then, if I take a look at the next one, 44,8, I'm going to say number of moles is volume over molar volume, and I land up with 2 moles of that ammonia gas. So it really doesn't matter what gas it is. If you're given the volume and you're at STP, it should again here say at STP, and you're given the volume at STP, you can always work out the number of moles. Then if they give you the number of moles and now they would like to know what the volume is, you can work that out as well, where you can simply say that volume is equal to number of moles times molar volume. So it is 3 times by 22,4, and you land up with 67,2 decimeters cubed. In this case, where you're given 28 grams of nitrogen, you're not given the number of moles, but it's easy to calculate the number of moles. Number of moles is equal to mass over molar mass. You know nitrogen is not in 2, so it's going to be 14 plus 14, and you land up with 28, and so that's just 1 mole. Now, if I substitute that into volume is equal to number of moles times molar volume, I get 1 times 22,4, and I get 22,4 decimeters cubed. What's starting to show itself is that we've actually got 3 equations that tell us the number of moles, which means that we've got 3 triangles. And then the triangles are number of moles or mass over molar mass. Number of moles is equal to number of particles over Avogadro's number. And finally, number of moles is volume over molar volume. A few things that are interesting to note. Firstly, number of moles is always in the denominator. Then we've got this thing molar mass, Avogadro's number, and molar volume. And they are always found, this is straight off the information sheet, it's a constant 6,02 times 10 to the power of 23. Molar volume, always 22,4 decimeters cubed at STP, and it's on the information sheet. And molar mass we found off the periodic table, which is on the information sheet. So in other words, these are always constants down at the bottom of the equation. And then the number up at the top is the given or the unknown little bit of information. What mass was I given? What number of particles was I given? What volume was I given? We can now equate all of these if we want to, and we can say something along the lines of number of moles is equal to mass over molar mass, which is equal to number of particles over Avogadro's number, which is equal to volume over molar volume. So all of those are equal to each other, and you need to be able to interchangeably use them. How many particles are there in 44 grams of carbon dioxide? So I'm going to let you pause this for a minute and try work through them, and then you can follow my instruction. Right, so the first thing that I need to do is I need to say number of moles is mass over molar mass, which is equal to number of particles over Avogadro's number. Substituting in that information, I'm dealing with carbon dioxide. I've been given 44 grams. Carbon dioxide is CO2, so it's 12 plus 16 plus 16, which happens to be, very conveniently, 44. And I am asked how many particles have I got, and I know that Avogadro's number is 6,02 times 10 to the power of 23. When I work that out, I find that my number of particles is going to turn out to be equal to 6,02 times 10 to the 23 molecules. And why am I choosing molecules? Because carbon dioxide is a covalently bonded molecule, non-metal. Then it says calculate the mass of 11,3 decimeters cubed. So mass is equal to, mass over molar mass is equal to volume over molar volume. Because I've been given a volume, it doesn't matter what gas I've got, I'm just simply going to substitute in the values. Mass is what I'm looking for. The molar mass, oh, it does matter what gas I've got because I'm looking for hydrogen gas. Hydrogen gas is H2, which means it has a molar mass of 2. 1 plus 1, not difficult. The volume that they give me is 11,2. The standard volume that is always at STP of 1 mole of gas is 22,4. I therefore land up with 0,5 and multiply that by 2. I can cross multiply. Mass turns out to be equal to 1 gram. Work through these and then I will quickly go through them. Press pause. Right, we're going to take a look at the number of atoms of potassium in 53 grams of potassium permanganate. So I am going to work out the following. So you obviously need to get the molar mass of potassium permanganate, and you're going to go 40 plus 55 plus 4 times 16, and you land up with 159. So number of moles is equal to mass over molar mass, and that is equal to 53 divided by 159, which equals 0,3 moles. You then say, how many particles of potassium permanganate have I got? I've got number of particles is equal to number of moles times Avogadro's number, 0,3 times 6 times 10 to the power of 23. So 0,3 times 6,02 times 10 to the 23. And I land up with 2 times 10 to the power of 23, but that is not what they asked me. I have landed up with 2 times 10 to the power of 23 potassium permanganate particles, the whole particle. They just want to know about the atoms of potassium. So what I do is I say, what's the relationship between potassium permanganate and potassium? And in this case, it's convenient. It's a 1-to-1 relationship. I have one potassium atom inside every potassium permanganate particle, and therefore the number is exactly the same. Let's do this one with the number of lead in 22,3 grams of lead oxide. So the first thing to do is to find the molar mass of lead oxide, and the molar mass of lead oxide is 207 plus 16, which equals conveniently 223. So now you're going to say that number of moles is equal to mass over molar mass, which is equal to 22,3 over 223, which equals 0,1. Therefore, number of particles is equal to number of moles times Avogadro's number, which is 0,1 multiplied by 6,02 times 10 to the power of 23. And I land up with 6,02 times 10 to the power of 22 lead oxide particles. The question wasn't lead oxide particles, it was lead, number of atoms of lead. But lead oxide is to lead as 1 is to 1. And so, as a result, if I have 6,02 lead oxide particles, I will have 6 times 10 to the power of 22 lead atoms. So that's how I get that answer. What about iron in 240 grams of iron oxide? So once again, number of moles is equal to mass over molar mass. And that's going to be 56 times 2 and 16 times 3. And altogether, I'm going to land up with 160 as the molar mass. I'm given 240. And so I land up with 1,5 moles. Number of particles is equal to number of moles times Avogadro's number, which is equal to 1,5 times 6 times 10 to the power of 23, or 6,02 if you prefer, and that's equal to 9 times 10 to the power of 23. Moles, at least not moles, iron oxide particles. But what is the relationship between iron and, sorry, I just need to make a bit of space, between iron, Fe203 to Fe is a 1. For every 1 iron oxide, I actually have 2 iron particles. So 9 times 10 to the power of 23 is going to become 18 times 10 to the power of 23 iron atoms. Determine the number of molecules and atoms in each of the following. Again, press pause, try work through, and then we'll look at the answers. So first we can work out the number of moles of iodine vapor. It's I2, so it's 127 times 2. Mass over molar mass, 254 divided by 254, you get 1 mole of iodine vapor. Multiply that by Avogadro's number, and I've got 6 times 10 to the power of 23 molecules of iodine vapor. But how many atoms of iodine have I got? Well, for every 1 iodine molecule, there are 2 iodine atoms, so I double that number. What about chlorine gas? Molecules, mass, at least volume, over molar volume, I get 0.25. Times that by 6 times 10 to the power of 23, 1.5 times 10 to the power of 23. But for every 1 molecule of chlorine, there are 2 atoms of chlorine. So I double that for the number of atoms. Finally, if I'm looking at the number of atoms in 2 grams of potassium sulfate, we'll press pause and work through it, and then we'll look at the answers. Now, these numbers aren't turning out quite as nicely as the last lot because they aren't pretty numbers. So you must remember to keep the numbers in your calculator and not get rounding errors. So mass over molar mass of potassium sulfate, and you land up with 0.01. Leave it in your calculator because it's got lots of blah blah numbers afterwards. Don't write them, but keep it in your calculator. Times 6 times 10 to the power of 23 gives me 6.8 times 10 to the 21. But that's the number of molecules. They're not molecules really, they're unit cells, but anyway, we'll go with molecules in inverted commas, potassium sulfates. For every 1 potassium sulfate, there are 2 potassium, so I double that number to get that answer. The next one, lead, I can work out 10 divided by, lead is 207 plus 16 plus 16, 239, you get 0.04, blah, 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 blah. Keep it in your calculator, multiply that by 6 times 10 to the power of 6.02 times 10 to the 23, and you actually come out with exactly 252 times, 2.52 times 10 to the 22. But for every 1 lead oxide, there's only 1 lead atom. So the number of particles is equal to the number of lead atoms. And finally, silver atoms, you've got 8 grams, 8 divided by 169, 107 plus 14 plus 48, and you land up with 0.047 blah blah blah. Keep the blah 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 in the calculator, multiply by 6.02 times 10 to the 23, and it turns out again for every 1 silver nitrate there is only 1 silver, and you land up with 2.84 times 10 to the 22.